Okay, so this is kind of a classic problem where we have a weight on what you would call a simply supported beam, and that means that there's a support on the left and a support on the right, and there is a force going down. And you're trying to find the reactions of the support forces. Okay, I'm going to redraw this down below. So I'm going to show you how to analyze this. Let's say this was like a 10 Newton. Oh boy. Okay, let's just draw it down here. This first situation. Okay, I got a support on the left, support on the right, and let's just make up a force, a 10 Newton force right about here. Now you can tell from the sections that there's 4 equal sections going across, and this weight is 1/4 of the way over. So if you wanted to use like algebra, you could break this into 4 sections. This is x, 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 x distance. All right, and we'll call this the reaction at A, and then we'll call this the reaction of the finger. Okay, so the force. So you know what? Let's label them F instead of reaction. That's my engineering background kicking in. Let's call this force at A and force of the finger. So this is the free body diagram on the beam. Now, we can actually solve for the reaction on both sides, even though we have 2 unknowns here. And the way you do it is you choose a point to sum the rotations or the torques. And it's easiest to choose a point that one of the arrows passes through, one of the unknown arrows. So I'm going to choose this point right here at A, and I'm going to sum the torques about that green dot, that point. So this 10 Newton force is causing a torque in this direction, and the finger force is causing a torque in the other direction. And they actually completely balance each other out because the beam is not rotating. It's not accelerating, right? It doesn't have any net rotation, right? If it did, right, net torque equals I alpha. If you did have a net torque, you would have angular acceleration, and clearly we don't. So you can actually say that the net torque must be equal to 0, the sum of the torques, right, which is the net torque. And there's 2 torques. There's the 10 Newton force causing a torque and the force of the finger. So don't forget the formula for torque is radius perpendicular distance r times the force F. Right? So we have that both for the 10 Newton force and the finger. So if I sum the torques, we'll just say that's torque due to the 10 Newton force plus the torque due to the finger. Okay, and now we'll actually substitute. We know that the value is 0 because it's balanced. The 10 Newton force would have a distance of x, and the force value is 10 newtons. And that's making it rotate in this direction, which we'll call positive. And then in the other direction, the finger for let's fix that. The 10 Newton force is making it rotate this way, which is going to be negative. And the finger force is a distance of 4x away, which is going to make it rotate in this direction, which we'll call positive. Okay. So now let's do the math. We'll ignore units for a second, and we'll remove 10x to the other side of the equation. Right, that's this portion right here. And then we'll say 4x times force of the finger. All right. So we're going to solve for FF. So we divide each side by 4x. And we get 2.5. So it's 2.5 newtons. That's the reaction of FF. So if we come back up here the force of the finger is 2.5 newtons. And you can kind of obviously figure out that this has to be 7.5 newtons, the force at A, because these two together have to balance with the other vertical force of 10 newtons.